All right, let's dive in. We've got a stack of material here about a concept so ambitious, so far out, it genuinely redefines the word skyscraper. This deep dive is all about the Analemma Tower, based on the sources you brought to the table. Our mission today, to cut through the incredible visuals and the sci-fi premise, understand the core idea, grapple with the absolutely monumental engineering challenges it presents, and figure out if this is a genuine blueprint for future habitation or, something else entirely, maybe more of a spectacular what if.
Exactly. We've looked at the original proposals from Cloud's Architecture Office, or CAO, and importantly, analyses that really dig into the physics and the engineering feasibility or, well, lack thereof. It's a brilliant example of where grand architectural vision meets the harsh realities of physics.
So let's open up this stack and explore the idea of a city hanging from the sky. So let's start right at the beginning. At its heart, what is this Analemma Tower concept?
Okay. It's a design proposal from Cloud's Architecture Office, CAO. The core idea is completely flipping the traditional skyscraper model. Instead of building up from a foundation on Earth, this tower would hang down from an asteroid placed in orbit around the planet.
Suspended from space. That just sounds wild right off the bat.
It absolutely does. CAO calls the system that anchors it the Universal Orbital Support System, or UOSS. Think of a captured asteroid in orbit acting as the anchor connected to the top of the tower by ultra-high-strength cables.
Right, cables. And CAO, they're known for really pushing conceptual boundaries, aren't they?
They are, yeah. Their portfolio includes other speculative projects, like a proposed Mars ice home for NASA. This Analemma concept isn't just a one-off. It fits into their exploration of architecture on entirely new, non-terrestrial frontiers. They themselves explicitly label it speculative space architecture, and it's widely referred to as a utopian thought experiment.
Okay, which explains why initial reactions from the sources range from crazy to wild to straight out of a sci-fi movie. So with that in mind, what's the architectural purpose they state for this design?
Well, their stated intent is quite bold. They want to overturn the established skyscraper typology. And, they say, cater to a human desire for extreme height, seclusion, and constant mobility.
So it's not just about building something incredibly tall, it's tapping into something else entirely. A feeling, maybe?
Precisely. That speculative nature, combined with CAO's background and their framing of it as a thought experiment, it signals that the primary goal probably isn't immediate construction. It's designed to be a conversation starter, to challenge our assumptions about where and how we can build and, make us think differently about humanity's future, both on and off Earth. Its real value might be less as a blueprint and more as a powerful conceptual provocation.
The sources mention potential locations like Dubai and New York. Why those specific places?
Well, Dubai is cited for its supposedly lower construction costs, 1/5 of New York, they claim, which is interesting, and also its experience with building massive structures.
Or they know super dolls.
Exactly. And New York comes up because the proposed orbital path is specifically calibrated to move slowest over the city, which could potentially allow for easier access or transfers, theoretically. The design inherently allows for global mobility as it travels along its orbit. But associating it with Dubai, a place famous for architectural ambition, might be a strategic move to lend it a touch of perceived realism, even if the core idea remains highly speculative.
Okay, let's step inside this hypothetical structure. What is the vision for living in the Analemma Tower? What's it actually like?
Well, first you have to picture the scale. It's conceived as a self-contained vertical city hanging down an astonishing 32,000 meters.
32 kilometers.
That's right, 32 kilometers. It would dwarf any existing building on Earth, reaching well up into the stratosphere.
That number is just wow. How would you even organize a city vertically at that height?
So the design sketches out distinct zones. The lower sections, closer to the Earth's atmosphere, are for business offices, dining, shops, that sort of thing.
Bookman?
Moving further up, about 2/3 of the way, are the residential areas. And then the highest reaches, between 17,000 and 20,000 meters, are proposed for spiritual activities, even a reliquary and a funerary section.
A whole life cycle, literally, high above the planet. That's quite a statement.
It is. And it aims for a degree of self-sufficiency, with dedicated garden and agriculture sectors integrated into the design.
What about the day-to-day experience for someone living there? The views must be something else.
Oh, utterly unique. You'd have constantly changing dynamic views of the Earth as the tower travels along its 24-hour orbital path. The windows, though, They'd have to be incredibly robust. Think about the extreme atmospheric pressure and temperature changes across 32 kilometers.
Yeah, huge difference between top and bottom.
Exactly. So they likely become smaller and more heavily reinforced the higher you go.
And there was that intriguing detail about extra daylight. How does that work?
Yes, that's pitched as a major proposed perk. Because you're so high up, above the densest part of the atmosphere, inhabitants, particularly at the upper levels, could get an estimated 40 to 45 minutes of extra daylight each day.
That's fascinating. But it also sounds like the environment outside would be incredibly harsh, like lethally harsh.
Extremely harsh. Yeah. We're talking outside temperatures dropping to minus 40 degrees Celsius, maybe even minus 56 C, and the atmosphere becomes a near vacuum as you ascend.
So stepping outside is basically an EVA.
Absolutely. Any activity outside the structure would require protective suits, similar to what astronauts wear. And, the design also fundamentally challenges our idea of a fixed place.
Yeah.
Hanging from a moving asteroid, tracing that global figure-8 path, the tower exists in a state of constant dynamic motion across the globe.
Right, it's not in the country.
Exactly. Its location isn't defined by national borders or city grids, but by celestial mechanics. It raises all sorts of questions about where you are if you live there. Nationality, jurisdiction, community, identity all become fluid concepts.
And the proposal seems to spin these incredibly difficult, even life-threatening environmental conditions into selling points. Almost luxury features.
It really does. It attempts to reframe these extreme conditions as features of a high-end experience. That 45 minutes of extra daylight and the ever-changing view are highlighted as major benefits. It's designed to tap into that desire for extreme heights, seclusion, and constant mobility that they mentioned earlier, with the expectation of commanding record-breaking prices because, as they note, sales price per square foot rises with floor elevation.
Wow.
The architecture is consciously trying to commodify the extreme.
All right, let's get into the really mind-bending part. How this thing could possibly stay up. It all hinges on this UOSS system, right? The anchor.
That's right. The core principle is suspending the tower from a captured asteroid using these ultra-high-strength cables. The architects point to space elevator concepts as the basis for the idea.
How is it different from the standard space elevator concept we hear about?
Well, a traditional space elevator is anchored firmly on Earth and extends upward to a counterweight, usually placed in geostationary orbit.
Geostationary meaning it stays over the same spot on the equator.
Exactly. It's held taut by balancing forces. Analemma completely inverts this. The anchor, the asteroid, is in space, and the structure hangs downwards towards Earth. And the proposed orbit for the asteroid isn't standard geostationary either. It's an eccentric geosynchronous orbit.
Okay, break that down. Geosynchronous means it orbits in 24 hours.
Correct. It stays synchronized with the planet's rotation. But eccentric means the orbit is elliptical, stretched out, and inclined relative to the equator, not a perfect circle staying flat. So instead of staying over one spot, it traces a figure-8 path over the globe every single day.
And that figure-8 shape is called?
An analemma. That's where the name comes from.
Oh, now the name makes perfect sense. Clever.
It is. And because the path is a figure-8, the speed of the tower relative to the ground varies. It moves slowest at the northern and southern turning points of the figure-8. The design specifically calibrates this orbit, they say, to move slowest over New York City.
As a transfer point.
That's the idea, potentially allowing for surface transfers during these slower phases.
There was some confusion in the sources about the exact altitude of the asteroid, wasn't there? Like 35,000 kilometers versus 50,000 kilometers?
Yes, that's a really key point. Some sources mention around 35,786 kilometers, which is the standard geosynchronous altitude. But CAO's own diagrams often show the asteroid much higher, around 50,000 kilometers.
Why does that matter so much?
Well, attaching a multi-million-ton tower like Analemma would drastically shift the entire system's center of mass downwards. Imagine the weight pulling it down. To counteract that shift and maintain orbital stability, the asteroid might need to be boosted to a much higher altitude, maybe that 50,000 kilometer mark, very quickly after the tower is attached.
So the energy for that boost
would be absolutely colossal, astronomical. This altitude ambiguity really highlights the immense complexity and perhaps some glossed over details in the orbital mechanics of the proposal.
So the physics of this long hanging structure, it can't just be a passive cable dangling there, can it? Especially dipping into the atmosphere.
Absolutely not. And this is where it gets really critical from an engineering standpoint. A traditional space elevator relies on a delicate balance of forces. The Analemma Tower, hanging 32 kilometers down into the upper atmosphere while in this weird eccentric orbit, faces significant atmospheric drag.
Like air resistance, even way up there.
Exactly, even in the thin upper air. As the tower moves, sometimes at speeds up to 300 miles per hour relative to that thin atmosphere, that drag would constantly pull on the system. It would cause the asteroid's orbit to decay over time, spiral inwards.
So it would...
Eventually, yes. To prevent this, the asteroid would need powerful, incredibly precise, and continuous station-keeping thrusters. Basically, small rockets constantly firing to push the asteroid back into its intended path, actively fighting against that drag.
Which means fuel. Lots of fuel.
Vast, likely unsustainable amounts of propellant. This makes it a highly active, fuel-hungry system, not a stable, passive tether like a simple space elevator might imply.
And that figure-8 path isn't just a necessity of the orbit, is it? You said it feels like part of the design statement.
It absolutely feels performative. By deliberately engineering those slow points over major cities like New York, the tower becomes a globally visible, moving landmark. It's like a kind of predictable celestial ballet, designed to maximize its presence and symbolic power, a deliberate aesthetic choice driven by the orbital physics.
Okay, so assembling this whole concept requires technologies that, well, let's be blunt, they don't really exist yet on the necessary scale.
That's putting it mildly, yes. It relies on a cascade of futuristic technologies, each one a monumental challenge on its own. First up, you've got the asteroid capture and relocation. The whole premise hangs on capturing a large asteroid and maneuvering it precisely into the specific, complex Earth orbit. The proposal sometimes points to missions like NASA's OSIRIS-REx returning a tiny sample, or past concepts for redirecting small boulders as, like, proof of concept.
But is that really comparable to grabbing a massive asteroid needed to anchor this thing?
Not even remotely. OSIRIS-REx returned, a few ounces? DART just nudged a small asteroid moonlet, capturing a large, massive asteroid, one heavy enough to anchor a skyscraper and maneuvering it precisely into a stable Earth orbit. That requires a level of technology and energy orders of magnitude beyond anything we have or can foresee in the near future.
What's the TRL on that?
Oh, the technology readiness level, TRL for this, is incredibly low, likely just 1 to 3.
So basic science, barely proven in a lab.
Exactly. We're talking basic principles, barely formulated, let alone having built a single working component at anything near the required scale. Okay, next big one, tether material science. The cable needs to be, tens of thousands of kilometers long?
And support a city's worth of weight.
Right. It needs to be incredibly strong, yet lightweight. The proposed materials are usually carbon nanotubes, CNTs, or graphene because of their amazing theoretical strength-to-weight ratio.
That sounds like a good direction theoretically.
Theoretically, yes, but the reality check is harsh. Manufacturing a continuous, defect-free strand of carbon nanotubes long enough and strong enough for this purpose is currently impossible. In fact, one analysis pointed out a fundamental material limit. Even the strongest theoretical carbon nanotubes would snap under their own weight if you made them longer than about 6,000 kilometers.
6,000 kilometers, and this needs to be much longer.
Way longer, and strong enough to hold the tower, too. This Analemma cable needs to be at least 6 times stronger than even that theoretical limit, and vastly longer. Current production yields for high-quality CNTs are minuscule, and we can't weave them into perfect kilometer-scale structures. Asking for millions of tons of carbon nanotubes just highlights how massive that technological gap is.
Okay, what about power? How do you power a city in the sky?
Power generation is proposed via space-based solar panels, either on the asteroid itself or on the upper levels of the tower. This is perhaps more plausible than some other aspects, as you get constant, unfiltered sunlight above the atmosphere.
More reliable than Earth-based solar.
Definitely. But scaling it up to power an entire city, distributing that power efficiently down 32 kilometers of structure, and maintaining vast solar arrays in the harsh space environment. Those are still significant engineering challenges. Then there's life support and environment control. This is unprecedented. Water is proposed via recycling within the tower and potentially harvesting from clouds or rainwater lower down.
Can you really harvest enough water from clouds for a city?
That's a huge question mark. The feasibility of harvesting sufficient water at altitude is really uncertain, and just maintaining a breathable atmosphere, stable pressure, and comfortable temperature over that entire 32-kilometer height gradient. With those extreme external conditions, the -40°C, the near vacuum means building a life support system of unparalleled scale, complexity, and reliability.
And just getting people and stuff up and down those 32 kilometers,
Yeah.
plus to and from Earth.
Right. Vertical transport inside the tower suggests futuristic cable-less electromagnetic elevators, like maglev trains going vertically. That tech is still in very early development. And transportation to and from the tower involves a mix of things. Specialized drones, high-altitude air transport, maybe even parachutes are mentioned.
Parachutes from 32 kilometers up. Yikes.
Yeah, and docking at those proposed transfer stations during the slow orbital points. The sheer logistics of reliably docking anything with a massive moving structure high in the atmosphere are unique hurdles we've never really faced. The crucial point here really is it's not just one massive hurdle to overcome. It's a cascade of monumental, interconnected advancements needed across multiple fields simultaneously. If any single one of these critical technologies fails or is significantly delayed, like finding a way to make that impossibly strong tether or capture that asteroid or build that life support, the entire concept, as proposed, becomes unachievable. It just falls apart.
So citing things like OSIRIS-REx is a bit misleading.
It significantly overstates the case, yeah. Those missions are fundamentally different in scale and purpose. And while asteroid capture and tether strength are often the headline challenges, these secondary systems like self-sufficient life support or power distribution at this scale are also enormous. They're often glossed over in the flashy renderings, but represent their own huge unsolved engineering feats.
Okay, so taking all that incredible vision and the, frankly, sci-fi level technology required, how does it actually stack up when we look at it from a cold, hard, practical feasibility standpoint?
Yeah. A rigorous feasibility analysis reveals a pretty profound gap between the ambitious vision and our current engineering reality. It's vast. Let's start with just structural and construction. The proposal mentions building the tower on the ground, say in Dubai, and then somehow lifting it into place.
Lifting a 32-kilometer tower.
It's widely considered impossible with current or even foreseeable technology. A structure that tall simply couldn't withstand wind loads or even its own weight while standing vertically on Earth, let alone being lifted perfectly vertically without buckling or just plain toppling over. And the stress introduced by transitioning from being compressed, like a normal building standing up, to being in tension, hanging down. That transition alone would likely introduce destructive loads.
So building it in space is the only real option, hypothetically.
Space assembly is the alternative, but think about what that entails. You'd need to launch an enormous, truly unprecedented mass of materials into orbit.
Far beyond anything we can launch now.
Far, far beyond current capacity, and then assembling a 32-kilometer structure in space, potentially using robotics or human crews, while maintaining stability during construction. That is an engineering feat of unparalleled complexity. We've never done anything remotely like it. Plus, the structure itself needs a design that works efficiently in both compression during some phases of assembly, perhaps, and tension when hanging, which is inherently difficult for something so incredibly long and slender. And as we keep coming back to, the fundamental issue of the tether material strength remains a complete showstopper. The required materials are orders of magnitude too weak. Period.
Okay, what about keeping it stable once it's up there, the orbital mechanics?
Yeah, orbital stability and dynamics are also massive problems. That eccentric orbit means significant north-south motion covering vast areas, and that atmospheric drag on the lower 32 kilometers as it slices through the upper air at high speed, it's substantial.
We talked about the fuel needed for thrusters.
Exactly. It would cause rapid orbital decay, pulling the asteroid and tower closer to Earth unless it's constantly counteracted by that massive continuous thrust from the asteroid. Requiring a truly unsustainable amount of fuel delivered somehow, it's just not practical long-term. And remember that instant shift in the system's center of mass when the tower is attached.
Right, the balance point shifts drastically.
It wouldn't just be a minor adjustment needing a little nudge. It would catastrophically perturb the asteroid's orbit. It could potentially put the entire massive system on a collision course with Earth, unless it could be instantly boosted to a much higher, stable altitude, with an amount of energy that's just extraordinarily powerful, far beyond anything we can currently generate or control precisely in space. Not to mention things like vibrations propagating down that incredibly long tether, or the subtle but cumulative gravitational pulls from the moon and sun. These are complex dynamics that don't seem fully addressed.
And I remember one critique questioning the specific orbital path shown.
Yes, exactly. One detailed analysis we looked at argued that the specific figure-8 orbital path depicted by CAO, conveniently passing over places like NYC and Peru, isn't actually physically possible based on the laws of orbital mechanics. Real orbits tend to mirror their northern and southern latitude extents. You can't just arbitrarily design them to hit specific cities like that. The physics dictates the path more strictly. The real path would likely extend much further south than shown in those beautiful renderings.
Okay, let's talk money. They mentioned building in Dubai for cost savings. Does that even register on the scale of this project?
This brings up what's been quite rightly called the paradox of cost-saving rationale. It's almost comical, suggesting lower conventional construction costs in Dubai saving maybe a few billion compared to New York seems utterly absurd when you juxtapose it with the hypothetical cost of the rest. We're talking about capturing a massive asteroid, developing entirely new supermaterials that don't exist, undertaking dozens, maybe hundreds, of heavy space launches, and performing unprecedented in-space assembly.
That's trillions, easily, if it's even possible.
Exactly. Multi-trillion-dollar hypothetical expenditures, assuming breakthroughs that haven't happened. The savings on conventional building labor or materials in Dubai become utterly trivial, a rounding error. The economic model presented seems to vastly underestimate the true scale of the required expenditure, completely bypassing standard project life cycle cost assessments you'd do for any normal large project.
And safety. I mean, what happens if something goes wrong with a 32-kilometer structure tethered to an asteroid?
The safety implications are profound and seem largely unaddressed or hand-waved away in the proposal. First, traditional evacuation for a civilian skyscraper population is just impossible at these altitudes. How do you get thousands of people down safely from 32 kilometers up in near vacuum?
Those parachutes don't sound very practical.
Highly impractical for large numbers of people trying to descend through extreme cold and lack of air. Then there's the massive risk from space debris. The tower and its tens of thousands of kilometers of cable present an enormous target area in orbit. A significant impact could be catastrophic.
And if the cable snaps or they lose control of the asteroid?
A catastrophic failure, like the cable severing or losing control of the asteroid's propulsion system, would result in the deorbiting of a 32-kilometer structure plus the asteroid. That's not just a building falling. It's potentially a globally catastrophic impact event. The scale is terrifying.
Plus the hazards for the inhabitants themselves.
Constant exposure to extreme environmental conditions, higher radiation levels than on the ground. And just imagine trying to manage global air traffic and satellite operations around a massive moving structure traversing vast swaths of airspace and near orbit daily. It would be a logistical nightmare on an international scale.
I remember reading one critique that labeled these showstoppers minor problems. That seems optimistic.
Yeah, ironically, labeling these fundamental physics-based impossibilities as minor problems really highlights a common tendency in some visionary concepts. It's a way to downplay insurmountable obstacles as if they're just engineering details that smart people will eventually iron out.
Yeah.
But in reality, any single one of these minor problems, like needing a tether material 6 times stronger than anything known to physics, or controlling an asteroid against atmospheric drag indefinitely, is a major barrier rooted in fundamental science that prevents realization.
And when you stack them all up,
Exactly. When you combine them, the cumulative effect makes the project, as envisioned, practically impossible with any foreseeable technology, maybe ever. Looking at a feasibility table derived from the sources, core components like the asteroid anchor, the specific orbital type, the tower height itself, the tether cable, the construction method, and access egress. They're consistently listed as highly implausible with current foreseeable tech, or simply currently impossible, rated at those rock-bottom TRL 1-2 levels. Even systems like power and water, while maybe based on slightly more mature concepts, TRL 3-4 perhaps, become extremely challenging when scaled for total self-sufficiency at this magnitude and altitude.
So, okay, given all these enormous, seemingly insurmountable practical challenges, what is the actual point of the Analemma Tower? Does it have any value beyond being a really cool picture?
Absolutely it does. I think it's crucial to see its value elsewhere. Despite the profound feasibility issues, it holds significant value as a thought experiment. CAO themselves frame it as planetary design thinking. It encourages architects, engineers, maybe all of us, to think beyond just designing buildings on Earth and consider operating on a truly global or even orbital scale. The concept of a globe-traversing orbit and harvesting resources directly from the atmosphere are examples of this expansive thinking.
It's been called a utopian thought experiment. What kind of discussions does it spark?
Well, it forces us to confront some pretty fundamental questions, doesn't it? What are the ultimate limits of architecture? What could urban living look like in a radically different future, maybe even off-world? What is our relationship with the planet itself? And how might we expand into space in really unconventional ways? It pushes creative boundaries, daring us to imagine the sky itself as, well, habitable real estate.
Hmm?
It definitely joins a long tradition of visionary architectural concepts. Think of Boulet's cenotaph for Newton, or Fuller's geodesic domes over cities, concepts that, even if never built, shape our imagination and inspire future thinking.
How does it compare to other big visionary structures people talk about, like space elevators or orbital rings?
Good question. It draws heavily on space elevator principles, obviously, but it inverts the foundation hanging down instead of pulling up. This adds the entirely separate, massive challenges of asteroid capture and dealing with that atmospheric drag, which a traditional GEO space elevator mostly avoids. An orbital ring, which you mentioned, is a different theoretical concept altogether. That's more like a solid ring built in low Earth orbit, maybe with shorter tethers or elevators connecting down. It's designed partly to overcome the extreme length and material strength needed for a single GEO space elevator tether. Analemma is a single hanging structure, not a supporting ring.
And compared to giant Earth-based concepts.
Right. Compared to other massive but still terrestrial concepts like the proposed unbuilt Tokyo Tower of Babel, imagine it 10 kilometers, or the Exceed 4,004 kilometers, Analemma's 32-kilometer height and its space-based foundation truly put it in a completely different category. It's fundamentally untethered from the Earth's surface.
So even these impossible ideas, the ones that break physics as we know it, can still be incredibly useful.
Yes, definitely. Particularly in fields like aerospace and architecture, where long-term vision is so crucial, ideas that are far beyond our current capabilities can act as powerful catalysts for research and development. By posing extreme requirements like, we need a cable material 6 times stronger than anything theoretically possible right now, they can stimulate targeted research in those specific, challenging areas. Maybe we can find stronger materials eventually, and the intense discourse they generate, the debates, the critiques, that can broaden our collective thinking about what might be possible decades or centuries down the line. It stretches the imagination.
And they say something about us, too. Our hopes and fears.
I think they often do. These kinds of megaprojects often reflect deeper societal aspirations and anxieties. Analemma, with its focus on extreme mobility, seclusion, and self-sufficiency. You could read that in different ways. Does it symbolize a desire for ultimate control, for creating a self-contained world apart? Maybe stemming from a pessimistic view of Earth's future for the elite few who could afford it? Or is it boundless optimism about human ingenuity and our ability to conquer any environment? It probably contains elements of both.
And the visuals are undeniably powerful.
The aesthetics are absolutely critical to its impact. The stunning visuals and serious eye candy, as some sources put it, are key to its power as a thought experiment. Those sophisticated renderings are designed to be spectacular, to capture the imagination, which can sometimes, unfortunately, overshadow or distract from a rigorous technical assessment. It looks so real you forget it breaks the laws of physics.
So critical engagement is key.
Exactly. Balancing that appreciation for the sheer imagination with a grounded understanding of the very real, very fundamental constraints.
So bringing it all together then, what's our final assessment of the Analemma Tower concept? Where does it stand?
Well, as a concept, as a piece of speculative architecture, it is undeniably breathtaking and spectacularly audacious. Full marks for vision. It succeeds profoundly as an architectural provocation, pushing the absolute limits of imagination about where and how humans might live in the future. However, the chasm between this incredible vision and the engineering reality is just profound. It's vast. The hurdles we've discussed are critical, and with current or even foreseeable technology, they appear insurmountable. We're talking about capturing a massive asteroid perfectly, developing tether material that needs to be orders of magnitude stronger and longer than anything that exists, structurally building and deploying a 32-kilometer structure which is impossible as proposed on Earth, and an unprecedented, almost unimaginable feat in space. Ensuring orbital stability against constant drag indefinitely, creating functional life support and access systems at an unbelievable scale. It's just hurdle after hurdle after hurdle.
The TRL is just way too low across the board.
Exactly. From a technical perspective, the integrated system is at an extremely low technology readiness level, firmly in that TRL 1-2 range for almost all critical components. Its foundational technologies, like large-scale asteroid capture for this purpose or manufacturing kilometer-scale defect-free supermaterials, are themselves stuck at these very low TRLs. So the likelihood of the Analemma Tower being realized as currently proposed in the foreseeable future, meaning decades, maybe even centuries, is exceptionally low. Virtually zero, realistically. It requires multiple fundamental breakthroughs in physics and engineering simultaneously, not just incremental advances we can plot on a graph. Many commentators simply, and probably correctly, conclude the technology doesn't exist yet and that it will never be built into reality.
But you still maintain it has that significant value as something more than just a failed blueprint.
Absolutely. I think that's the right way to look at it. Despite its profound impracticality for construction anytime soon, or maybe ever, it remains a potent catalyst for thought. It pushes vital discussions on the future of architecture, urbanism, human expansion into space, and the kind of sustainable technologies we'd need for such radical endeavors. It serves as an extreme benchmark for that planetary design thinking, inspiring other ambitious ideas that might be slightly less impossible, maybe stepping stones. As one source nicely put it, even if the tech isn't here, we can still dream, though, right? And there's value in that dreaming.
It's like a modern myth.
In a way, yes. It serves as a kind of modern Icarus myth, a powerful expression of humanity's deep-seated aspiration to escape earthly limits, to build towards the heavens, to achieve the impossible, but one that also starkly reminds us of the unforgiving limits imposed by technology and, more importantly, fundamental physics. It's a tale reminding us to balance those grand, necessary dreams with a rigorous, honest understanding of reality and first principles. And, even purely conceptually, its sheer audacity forces us to redefine fundamental ideas. What is a building when its foundation is literally in orbit? How do we measure height relative to a constantly moving ground below? Traditional language almost fails. So in its audacious unbuildability, Analemma paradoxically helps lay some conceptual groundwork for future structures that might one day not be based solely on Earth. It pushes the definition.
And that was our deep dive into the Analemma Tower. Wow, what a concept. A city hanging from an asteroid. Just incredible to think about.
A truly visionary idea, absolutely. It pushes the boundaries of what we even think is possible to imagine, even if it currently crashes hard against insurmountable engineering realities.
It certainly makes you think about the future, doesn't it? About the kind of incredible things we might aspire to build and the monumental, almost scary challenges that lie ahead if we ever truly try to leave the ground like that.
It really does, and it raises some fascinating questions for you, the listener, to maybe ponder. If we could somehow overcome all those engineering hurdles, wave a magic wand, and build such a structure, what would actually happen to our traditional ideas of place, nationality, or jurisdiction for its inhabitants, constantly moving across the globe, belonging nowhere and everywhere? And maybe more profoundly, what does the very desire for such extreme height, such radical seclusion and constant mobility, essentially designing a world apart, hanging high in the sky, reveal about us as a species, about our aspirations, or maybe our anxieties?
Powerful questions to chew on indeed. Thanks for joining us on this deep dive exploring the incredible vision and the complex, challenging reality of the Analemma Tower.